All right, good afternoon, everyone. Trust you had a good and restful weekend. We're down to 2 topics to complete the module. So let us get started. I trust you have, before we get started, I trust you have seen the design project assignments that have been posted, and the solution to Friday's test. All right, those are the only 2 updates I have online. Okay, so let us get started. So today we want to talk about transfer function. All right, network analysis. It will incorporate a lot of what we have already done in terms of the various methods methods that we have applied to the circuit analysis, both for networks 1 and networks 2. All right, but we're just going to take a slightly different approach. Some of the stuff I will not go into in a lot of detail, because I know that at this stage not everyone would have completed Laplace transforms from math. So I won't go into those details. But anyway, let's get cracking. All right. So the first thing I want to talk about is the application of Laplace to circuit analysis. Yes. How does Laplace transform help us with circuit analysis? Okay. So to date, we have been focusing on operating within the time domain. But the Laplace transform facilitates the transition from time to frequency domain for easy analysis. On the surface, that may not mean a thing. However, we're going to delve in it a little more. So, in essence, Laplace is really just a tool and not an end in itself. Mathematically, the Laplace transform of a function is given by Laplace of the function f of t is equal to the integral from 0 to infinity f of t e to the minus st with respect to t. Now, I said earlier that Laplace was a tool, and this is similar to us using logs to help with multiplication. So we know if we have the same base, then we can add the logs if we're multiplying, or subtract the logs if we're dividing. Similarly, when we're dealing with vector quantities, we can look at them in polar form, yes, but we can also resolve them using complex numbers, and then go back to the normal way of presenting these numbers. So, as we have said, well, at least in networks 1, that complex numbers is really a tool, and we have stressed that in some of the questions that we may have asked, where we ask you for the current supplied, and persons would give an answer in complex form. But you know, complex number is a concept, and so we are not able to measure that complex number, but we are indeed able to measure the polar quantity. So the Laplace must be considered in that sense, that it's really just a tool, it's just a method of carrying out the analysis, and we are moving it from the time to the frequency domain. Yeah. Everybody have what's on screen? Does everyone have what's on screen? All right, I suppose silence means yes.
Yes, sir.
All right. So in converting from the time to the frequency domain, the Laplace of f of t is given by f of s. Yes? And what we want to do is to first look at how do we treat circuit elements in the time domain, how we treat them in the frequency domain. All right. So when we look at resistors, how do we treat them in the time, and how are we treating them in the frequency domain? Same thing with inductors and capacitors. And once we have that clear in our minds, then what we're about to discuss this afternoon into this evening will become quite simple. All right. So we're going to be looking at how each element is described within the frequency domain. Okay, so we start with the resistor. So resistor representation. Now from Ohm's law, we know that V is equal to IR. And given that the resistance R is a constant, then when we find the Laplace of V, and of course the Laplace of I, since R is a constant, then that will remain. So the impact would only be on I and V, so to speak. Okay? And so the Laplace of V, which is equal to IR, which of course would then be the Laplace of IR, implies that V is equal to IR, where big V, and I want us to bear in mind, if we go back to something that I believe we are all familiar with by now, we're using lowercase v and lowercase I, so it means that we are dealing with instantaneous values. The fact that I'm talking about instantaneous values is an indication that we are looking at it as far as the time domain is concerned. So moving from the time to the frequency, the Laplace of V being equal to uppercase V. So V would be equal to the Laplace of the instantaneous voltage, and I would be equal to the Laplace of the instantaneous current. All right. So from Ohm's law, we know that that is true. So in terms of physical representation in the time domain and in the frequency domain, what we have is that, do we have this?
Yes, sir.
All right. So what we have is that for the time domain, V is equal to Ri. Yeah, so we have our resistor with a current passing through it, and the voltage is given by R times I. And what we're saying is that in terms of the frequency domain, the same representation is used, where we have R, that's our constant, yeah. And then of course, the Laplace of I, so we are moving from lowercase I to uppercase I, and from lowercase v to uppercase V. All right. So when we transfer our resistor from the time to the frequency domain, in effect, what we're saying is that it remains the same. And the relationship, the Ohm's law relationship, also remains the same. All right, now, if we consider an inductor, for an inductor, for an inductor which has an initial current of I0, and we know how the inductor operates, yes? The time domain equation for the voltage across the inductor is given by V, which is equal to L di dt. And when we take the Laplace of this expression, right, so we're taking the Laplace of both sides, then we have V being equal to L into Si minus I at 0 minus. Of course, we know that I at 0 minus, because we are dealing with the inductor, I at 0 minus would be equal to I0. Yes? So V is equal to SLI minus I0. And we can rearrange this equation to make I the subject. So if we rearrange to solve for I, right, we get I to be equal to V over SL plus I0 over S. And so we can represent the inductor using two circuit representations. So based on what we have here, for the first equation, if we have a voltage here, yes, and it is equal to SLI minus Li0, then this is telling us we have a series circuit, because each of these, since it's equal to a voltage, then each of these would represent a voltage. Yes? And if we rearrange to make I, then of course each of these would represent a current. Right? So of course this would be a parallel representation.
Sir,
All right.
Sir. Sir.
All right. Can we move on?
Sir.
Yes.
You can repeat or explain what you mean by the series and parallel, please. I don't think I'm seeing exactly what.
This is a voltage. All right. It's coming from this. So we're taking the Laplace of this. So we have a voltage, and it's equal to the sum of two quantities. So if I'm going to represent this as a circuit, yeah, then it means that we have two elements in series. Because it means that each of these quantities must represent a voltage.
Yes, sir, I see it.
All right. And here we have a current, we have two quantities. So each must represent a current. Therefore, we'll have a parallel representation. All right?
Yes, sir. Yes, sir. Thank you.
No problem. So if we represent these diagrammatically, then this was our original circuit, yeah? And what we did just now, we used the voltage representation in order to find this, and then we rearranged this. We rearranged that to that. However, from this expression, yes, I could have had this. Yep. Which would have given me that. So there are different ways we could have arrived at the same thing. Now, what I want you to take note of is that let us assume that the initial current through the inductor is 0. Yes? We assume that the initial current is 0. Then it means that this would be eliminated and this would be eliminated. So the voltage source and the current source would be eliminated. Fair enough? Now, if those are eliminated, what we are left with are, well, what we're left with is, sorry, an inductor, which is SL. All right? So the comparison that I want you to take note of is that within the time domain, the inductor is L. When we transfer it to the frequency domain, it becomes SL. So that's the key. So we draw a circuit within the time domain. When we redraw the circuit in the frequency domain, the inductance becomes SL. Okay? Any questions? All right. Do we have this?
1 second, sir. All right, sir, thanks.
Okay. All right, so we have looked at the resistor, we have looked at the inductor. We want to know, look at how we represent the capacitor. So again, we're using that when we're looking at transients, yes? So for a capacitor with an initial voltage V0, the current I would be equal to C dV dt. As we did with the inductor, if we take the Laplace of this, yes, then we get I to be equal to CSV minus V at 0 minus.
Sir,
Yes.
sir, all the Laplace turn to that, sir. I'm not sure you get it.
Pardon me?
I don't understand how the Laplace transform of that turn to that. You can't really see the transformation.
Did you join the class when we gave the expression for the Laplace transform?
Yeah, you said it f of s e to the minus xt dt. So
Pardon me?
you say the Laplace transform of something is equal to f of s times e to the minus xt dt. Integral from 0 to s. Something.
Okay, so you integrate from 0, integrate this expression from 0 to infinity, e to the minus st. All right? If you haven't done it in math yet, then my apology, but I'm really not here to teach you math. All right? So you do the integral of this expression.
Okay.
All right. We can do the same thing as before, meaning look at the voltage expression. All right? So for the voltage expression, making V the subject. All right? We have V to be equal to 1 over SC times I plus V naught over S. Okay. Again, because we are dealing with voltages, yes, because we are dealing with voltages, it means that this would represent a series connection, and up here for the current, then we are also dealing with a parallel. All right, so we can have both parallel and series representation. Okay, so we are going to show these as circuits. All right, so for the voltage and the current, again for the capacitor, in the time domain, this is my capacitor. For the voltage, right, we had 1 over SC times I, and we have V naught over S. So we have V naught over S, yes, and we have 1 over SC, yes. So that's 1 over SC times I. This is our current. So the current is flowing through the capacitor. It's represented by 1 over SC. For the parallel representation, remember here we had SCV. All right? So with a voltage across this capacitor, if I want the current over here, then I'd have V divided by 1 over SC, which would have given me V SC, okay? Which is what we have here. That's VSC or SCV, whatever you want to say. All right? And then, of course, this would be the current source. Again, if we were to remove the initial conditions for the capacitor, as we did with the inductor, because remember with the inductor, we said, let's make I0 0. If that is the case, as with the capacitor, we were making the capacitor uncharged, right? Then if we take that out and take this out, what we are left with is that the capacitor is represented by 1 over SC. All right? So the three representations we now have for our components, right? R remains R, L becomes SL, and C becomes 1 over SC. And in essence, that's what we need to consider right, in dealing with this particular topic. So just to summarize, if the initial conditions are 0, then the circuits would be reduced to SL for your inductor and 1 over SC for your capacitor. So that would be the representation for your inductor and your capacitor. All right.
Sir, can go back 1 second, sir.
All right. Do we all have this?
1 minute, sir. Please.
No, sir.
Okay. So once we have done these representations, there are a couple other points I need to make that will guide your analysis of circuits within the frequency domain. So I want to make a couple comparisons between the time and frequency domain circuit analysis. And once you have that under your belt, you're fine. You're good to go. All right. Can I move on now? Now, given this, given the fact that the initial conditions are zero, meaning I0 is 0 or VC is 0 is 0, with no initial energy, the relationship between the terminal voltage and the current is given by that expression. Nothing fancy. So in the Laplace or in the frequency domain, the voltage in the frequency domain is equal to the impedance times the current in the frequency domain. It's not different from what we would have expected in the time domain. Where Z is the S domain impedance of the element. No, because this is true, and these points I wanted to, write them down, highlight them if you need, underline, put them in red. Just make sure that you appreciate these points. Now, we said here that this is the estimated impedance of the elements, meaning that based on how the resistor and inductor and capacitor are arranged in the circuit, you still have to go and find the combined impedance, so to speak, yes, of these elements. So whether it's a parallel series circuit, you name it, just that you represent it in the frequency domain based on what we just discussed, right? R remaining R, L becoming SL, and C being 1 over SC, all right? Once you have done that and you find the impedance, then you can apply this rule as you have been doing for the last year or so. Okay, now because this is true, we can then make the following point. So the rules governing circuits in the time domain are applicable to circuits in the S domain. What do we mean by that? All this is saying is that Kirchhoff's current law remains true. The voltage law remains true. If I'm doing star delta transforms, those remain true. So all these principles will remain true. The key, however, is that I must represent the components appropriately in the frequency domain. And by that, I mean L being SL and C being 1 over SC. Are we clear on that? All right. Any questions?
Can you repeat what you said, Aldo, please?
All right, so I'm saying all the rules, KCL, KVL, deltas, star delta transforms, are all applicable in the frequency domain. The only caveat is that the elements are appropriately represented. And by that I mean the resistor, we just went through the representation for the resistor. So the resistor remains. The inductor becomes SL, and the capacitor becomes 1 over SC in the frequency domain. So once you have those representations in the frequency domain, you can then apply these general rules. So if KCL is true in the frequency domain, it also means that nodal analysis is applicable in the frequency domain. If KVL is true, then it means that mesh analysis is also true in the frequency domain. All right? So all those principles that you have been learning from networks 1 into networks 2 are all applicable. Just that the element representation needs to be correct. Okay? So that's it for representation. The next thing we want to talk about now is transfer function. And what do we mean by that? It's nothing fancy, yes? So by definition, the transfer function is the ratio of the Laplace of the output to the Laplace of the input. Right? So your transfer function, H of S, is a ratio of PS over QS, where PS is the output and QS the input. That's it. Now, transfer function, it is the transfer function once we determine what we want to call the input, and we also determine what is the output, then we can define the transfer function. All right? So don't get hung up on this definition. All right? Just bear in mind that it is Laplace of output over Laplace of input. But input and output will be defined. All right? Now we can try and talk this one through until the cows come home. But this time around, I'm just going to jump into a simple example. And for those who have already done Laplace transforms, you would see, some of the benefits of using this tool. Okay, so let's jump into it. So derive an expression for the transfer function for the circuit below, given that the transfer function is defined as I over Vg. So the circuit current over the circuit voltage. That is how we are defining the transfer function. The output being the Laplace of the current and the input being the supply voltage. All right. And if you note, I've already shown L and C in the frequency domain. Now, before we jump into this, what kind of circuit is this? How are the elements connected in this circuit?
Series.
All right, so we have a series circuit. And if we have a series circuit, how do we find the current?
Total voltage over the total impedance.
All right, so I is equal to the voltage over the impedance, the total impedance. All right, so based on the statement we made earlier, that's a simple application of Ohm's law. Fair enough? And that's what we're going to do here. So I times the impedance will be equal to V. Does everybody have the circuit?
Yes, sir.
So that's the expression. Vg is equal to I times R plus SL plus 1 over SC. But the transfer function that we defined was I over Vg. So if I want I over Vg, all right, then I have 1 over R plus SL plus 1 over SC. And I can simplify this expression by multiplying what we have over here by 1, but I'm going to write 1 as SC over SC. All right? So I wouldn't have changed anything. If I do that, then I get that expression. Now, in doing this particular topic, under normal circumstances, I would have had primarily level 3 students who would have done some control systems by now. So a lot of this may not seem as foreign. Right? So you'd have taught some control systems. You would have, of course, completed, I think it's Math 3. Right? But I'm using this particular example to highlight a couple other things. Once I have the transfer function, yes, I want to determine what we call poles. Everybody have the expression? All right?
Yes, sir.
We want to determine poles and zeros for the network. And what poles and zeros really tell us is we're able to determine the type of damping that is within the circuit. So we'll know whether or not the circuit is going to oscillate, whether or not it's going to be overdamped, etc., or under or critically damped, etc., etc. So one approach, if you recall, when we were looking at transients, and if you look at the circuit that we just dealt with, yes, if we were to find the inverse Laplace of the final expression that we'll be looking at, if we were to find the inverse Laplace, then of course you would get the exponential or the exponential expressions that we would have derived when we look at transients, okay? So for those who have done Laplace transforms, then that would not be an issue, okay? Of course, you have your whole list of inverse transforms etc. So I'm not going to introduce that in networks too, because it's not what we need to be focusing on. We want to just look at the quote unquote networks aspect of it. So what's a pole? A pole represents the values of S that makes the transfer function infinitely large. If the transfer function is going to be infinitely large, it means that the denominator of the transfer function is 0. Right? So the poles represent the values of S that makes the transfer function infinitely large. And the 0, as the name suggests, represents the values of S that makes the transfer function equal to 0. So it would be the values of S in the numerator that makes its value 0. But there's a big question here. At what point do I determine that numerator and denominator values? All right? And that's the kicker that we need to focus on. So the poles makes it infinitely large, or in other words, where the denominator is 0, and the zeros makes the function 0, which in other words is the numerator being equal to 0. And the condition in making that determination, the condition that you need to assess the condition that you need to assess is, and this is what you now need to, as we did before, this you want to write and highlight and underline, write in red, because it's key. So before you determine the poles and zeros, you must reduce the equation in the denominator to have the highest order of S having a coefficient of 1. All right. So the highest order in the circuit we just looked at, the highest order of S was 2. So we had S squared, yeah? So we would need to make the coefficient of the S squared 1. And once you have done that, then you can solve the denominator, the equation in the denominator for the S value, yes? And similarly for the numerator. So if we go back to the equation that we just developed, we know that the transfer function was given by SC over S squared LC plus SRC plus 1. And in order to determine the poles and zeros, I would be dividing, because I want to make this coefficient, the coefficient of S squared 1, I would have to divide throughout by LC. So if I divide everything by LC, right, or in other words, multiply both numerator and denominator by 1 over LC, yes, if I do that, then I get this expression. And for the discerning person, you will see that this particular equation in the denominator looks quite familiar. Okay? So H of S would be S over L, S squared plus S times R over L plus 1 over LC. So of course, the poles would come from the roots of this equation. All right? So the roots of the denominator, which would be S1 and S2, okay? S1 and S2 would give me the poles, and of course, in this instance, the 0 would be 0, because with S being equal to 0, yes, we would have the function being 0. All right. Now, are we comfortable with this? Okay, now if I remember, I said earlier that the transfer function will be defined. I initially said that the transfer function was I over V, yes? But we could have defined it, however we wanted. If we were looking at the output across the capacitor, if we were looking at the output across the voltage across the inductor, or the voltage across the resistor to the supply voltage, we could have done that, yes? And so if we redefine, or if we were to define the transfer function, say VC over G, or VG, yes? And if we're doing that, then, this would basically be, we could use voltage divider, yes? And if we did that, then it would be 1 over SC, R plus SL plus 1 over SC, all right? And this is using the voltage divider rule. Again, as before, if I multiply both numerator and denominator by SC, yes, then I end up with this expression. Of course, the denominator remains the same, but there's a change in the numerator. So I could remember now, in order to find the poles and zeros, we need to make the coefficient of S squared 1. So I'll have to divide throughout by LC. If I divide throughout by LC, then this is my transfer function. So H of S is equal to 1 over LC, S squared plus SRL, R over L, sorry, and plus 1 over LC. Now, I am certainly not expecting you to sit down in an exam setting trying to do quadratic equations by longhand. I'm certainly not expecting you to do that. So obviously, you would be best. It would be best for you if you had a calculator that can easily solve these equations. All right. As you're aware, there are no restrictions in terms of calculators for this particular module. Okay, so we're going to move away from all this L and C and R. I'm just going to put in some numbers, and I'm jumping straight into a question that I took from a past paper a couple years ago. All right, so let's see where all of this takes us. Before we go there, any questions? Any questions? All right. So take this question from me, please. All right. So what's the first thing that we need to do? Anybody?
So convert to the frequency domain.
What do you mean by that?
So change the capacitance to 1 over SC and the inductance to SL.
Okay.
SL.
So we need to first redraw the circuit in the S domain. All right. So the 50 millihenries would be 0.05. So we have 0.05 S. And for the capacitance, we have 1 over 10 to the minus 6. So we have 10 to the 6 over S. All right. Now, we defined the transfer function as V0 over Vg. All right? So before we start throwing all sorts of math at this, any suggestion as to, you know, how we are going to get V0 and Vg in the mix?
So I can probably write V0 as a function of Vg, which should have been that in a group the 250 ohm with the inductor value, and then do the parallel connection with the capacitor, and then find the Poland. Yes, sir. Sir, may I forgot?
Yes, anybody else?
Yes, sir. Following up on what you were saying, we could use the capacitor, the branch with the capacitor and the branch with the inductors in parallel, and then use voltage divider to find the voltage across the capacitor.
All right, no, that's fine. That's fine. That's fine. Anybody want to think of my preferred method? Is there another way of doing this that, you know, since we're going to be dealing with some fractions, any suggestion?
Sir, could we use like nodal analysis or something like that, sir?
And that's where I would expect us to go. And since we're going to use nodal analysis, how would you set that up? By the way, what was said earlier is correct. So let me ensure that I made that clear. All right. But if we're using nodal analysis, what do we do? Who said nodal analysis?
Right, sir. You'd put the node right at the where the 1000 in part. First, you would like define your grounds, and after that, you'd like define which node you're working from. So, sir, I'm really learning of experience, sir.
No, man, then you can't give me a method. I don't know if you explain it. Anybody can have him?
So
Anybody else?
we're using nodal analysis. Where due to the fact that we're using nodal analysis, we're going to place the node beside the 1000 resistor and equal everything as a reference.
So all of this is a node.
Yes, ma'am. Yes, sir.
All right. So my reference is down here.
Yes, sir.
All right. So what would be the node voltage up here? Come on, it's not that hard. It's right before you, you know. If this is the reference, what's the voltage up here?
So is it V0?
Yeah, it must be V0. Because how do we define a voltage?
Oh, okay.
Eh?
Okay.
How do we define a voltage? It's not okay.
The voltage is I times the impedance.
No. How do we define a voltage? We talk about a voltage. What does that mean?
The potential difference between 2 points, sir.
Okay. So if the reference, what's the potential at the reference?
0.
0. So if down here says 0, then the potential up here says it must be V0. All right? Remember I said earlier, you know, all the principles that we have learned before are applicable. All right? So since this is V0, since V0 is the potential difference between these 2 points, if we make down the bottom 0, then it means that up here is V0. Everybody comfortable with that? Is there anybody who is unsure of what I just did? So that's a golden silence. So based on this, and I'm assuming you have already redrawn the circuit and put in, redrawn the circuit in the frequency domain, all right? So once we have done that, then we can now write the nodal expression. So V0 minus Vg over 1000. We agree with that? V0 over 250 plus 0.05 S plus S V0 over 10 to the 6. Okay? And then we remember our objective is to get V0 over Vg. So I want to put all the V0s together and I want to have Vg by itself. And then we can just factorize. So that's my objective. How I get there or how you get there is up to you, but I'm rushing there using this. So I just move the Vg over 1000 to the right hand side and I have V0 on the left hand. I want V0 over Vg. All right. So I do a little clean up first. Now, students, I'm going to declare up front that this is the real challenge in this topic, that you just have to be on top of your fractions. Imagine that. A whole topic comes down to fractions. Are we finished with that?
Yes, sir.
Okay. So we simplify. So I now have my VG over V0 over VG. That's the expression. Of course, I'm not inverting as yet. I want to simplify the expression before I invert. All right, that's just my approach. If you find it easier to do otherwise, then feel free so to do. Okay. So this so using this as the LCM. All right, that's how we go to that expression. All right, so we have it here. That's times 1. And then this is times S over 10 to the minus 3. All right. And remember the objective. Before I do any, before I try to determine the poles or the zeros, I first need to make the coefficient of the highest order for S 1. All right. So we're dividing through by, or we're factorizing the 50 times 10 to the minus 6. And so that now becomes my transfer function. All right, so note I have inverted here. Yes? So I've inverted and at the bottom I've simplified. So it is at this stage, now that I have made the coefficient of s squared 1, once I've gotten to that point,
Hello?
all right, once you have gotten to this point, do we have this?
That's it.
So if we simplify a little further, all right, we get 1,000 to s plus 5,000, and we have that as our denominator. So for our zeros, off the bat, our 0 would occur at s being equal to minus 5,000. It is for the, I'm not, well, tell you what, whatever method you choose to solve the denominator, that's up to you. I'm just going to give you use the quadratic formula for that. Yes. So if you were to use a quadratic formula, then that would be it. But of course, you also have the option. If you are going to use your calculator to solve the polynomial, then it is important that this must be shown. So once you have gotten there, if you want to just move from there and give me the solution, I'm fine. There's no need to go into the using the quadratic formula. So we're not teaching high school math, all right? So the poles will be minus 3,000 plus J4,000, minus 3,000 minus J4,000, right? So they are complex, yes? And the zero would occur, as I said earlier, at minus 5,000. All right, any questions?
Sir, when you say zero occurs at minus 5,000, sir?
Go again?
Why does the zero occurs at minus 5,000?
It's what makes the transfer function zero.
All right, sir.
The
Understood.
value of S that makes the transfer function zero.
All right, sir.
All right. So you look at the numerator in determining that value. All right. Okay. Now, I could go try 10 of these. If you are not able to put pen to paper and get it done, then it will not help anybody. So, what I want you to do is to take the next example, and you're going to work it through. As a matter of fact, just to get some accountability, why don't I ask you to upload it? All right, so we'll make you upload this prior to the class on Wednesday, all right? So just take the question while I deal with the register. And like the previous question, this is one that came directly from a past paper, right? Okay. Today is the 20th. Adams. Adams. So Adams not there? Uh-huh.
Hello?
I'm listening.
Yes, sir. In regards to what I was trying to explain with the tests and over the weekend, sir, what would be...
No, man, I'm not taking anything on that right now. I'm speaking about the what is before us.
Sir, but...
Mr. Wilson.
Respect, sir.
Mr.
Sir,
Wilson.
Sir,
all right, students, if there are no further questions, that's it for today, okay?
Sir.
Yes, Mr. Lewis.
Sir, earlier on, sir, I was having issues with the internet, sir. So I missed the all of the first part of the class, sir. Would the video be uploaded, sir?
Yes, it will.
Okay, sir. Thank you, sir.
You're welcome. All right, so that's it for today.
Sir.
Uh-huh.
Would you accept a question about the assignment, the group assignment.
Go ahead, sure.
Well, it's not even mainly about the assignment, but the grouping. For those who was not in a group for whatever reason, would it be too late for them to join a group or be put in a group?
There are only 2 individuals who will have the possibility of well, they can go into a group if they so desire, because the persons that they had originally grouped with have dropped the module. I believe it's Miss Ellis and Miss Lynch. So if they want to work together, fine. But everybody else will be working as individuals.
Okay, sir. Thank you.
You're welcome.
Oh, one question, sir. So I just trying to understand what you're saying, because I saw the notice on the assignment, but I realized that I was not in any group. So you're saying I'll be working individually?
Yeah, man.
Okay, sir.
Yeah, man. Okay. All right. All right. Have a good evening, everyone. And we'll go through this on Wednesday, but I need you to go through it on your own. Yeah, I want you to go through it on your own in preparation for Wednesday. All right. Have a good evening.